Welcome to this course on linear interpolation and extrapolation. In this training, we will explore fundamental mathematical techniques used to estimate values within and beyond a known set of data points. Interpolation and extrapolation are widely used in engineering, physics, data science, and many other fields to predict unknown values based on existing information. Linear interpolation helps us estimate values between two known points, ensuring smooth transitions in data. Extrapolation, on the other hand, allows us to extend our predictions beyond the available data range. This course will break down these concepts step by step, using clear explanations and practical examples. By the end, you'll have a solid understanding of how to apply linear interpolation and extrapolation in real-world scenarios. Let's get started. Now, let's define two fundamental concepts, linear interpolation and linear extrapolation. Linear interpolation is the process of determining a new data point within the range of existing data points. Given two known points, we estimate an intermediate value along the straight line connecting them. In the graph on the left, point P is an interpolated value between points A and B, meaning it lies within the known data range. On the other hand, linear extrapolation is used to estimate a new data point outside the given range. Instead of staying within the known data points, we extend the trend beyond them to predict an unknown value. In the graph on the right, point P is an extrapolated point that lies outside the range of points A and B. From a mathematical perspective, both interpolation and extrapolation involve finding the value of y for a given x, based on two known points, x1, x2, and their corresponding values, y1, y2. These techniques are widely used in engineering, physics, and data analysis to estimate missing or future values. In the next section, we'll explore the formulas that make these calculations possible. Now that we understand the concept of interpolation, let's go step by step through the mathematical process of calculating an interpolated value. Step 1. We start by identifying the given data points. These are two known points, x1, y1, and x2, y2, which define a straight line. Step 2. Now we calculate the slope of the line, denoted as m. The slope represents the rate of change between the 2 points and is given by the formula, m equals delta y divided by delta x equals y2 minus y1 divided by x2 minus x1. This formula essentially measures how much y changes for a given change in x. Step 3. Now we determine the x-coordinate of the point where we want to interpolate. This is simply the value of x for which we need to find the corresponding y value. Step 4. Finally, we calculate the interpolated value y using the equation, y equals y1 plus m times x minus x1. This formula allows us to find an estimated y value that lies along the line between the two known points. By following these steps, we can accurately determine intermediate values using linear interpolation. In the next section, we will apply these equations on two examples, one for interpolation and another one for extrapolation. In this example, we are given 2 points, 1, 2, and 5, 7. Our goal is to calculate the value of y when x equals 2. Let's go step by step. Step 1. First, we extract the coordinates of the given points. We have x1 equals 1, y1 equals 2, x2 equals 5, and y2 equals 7. Step 2. Now, we determine the slope of the line passing through these 2 points using the formula, m equals y2 minus y1 divided by x2 minus x1. Substituting the values, we get, m equals 7 minus 2 divided by 5 minus 1 equals 1.25. Step 3. Next, we write down the x value where we want to find the corresponding y value, which is x equals 2. Step 4. We now calculate the interpolated y value using the equation, y equals y1 plus m times x minus x1. Substituting the known values, we get, y equals 2 plus 1.25 times 2 minus 1 equals 3.25. So, when x equals 2, the interpolated y value is 3.25. Since the x value we are interpolating for lies between our given x values, this is called interpolation. This method is useful for estimating values between known data points in a linear trend. In the next section, we'll explore how this method can be extended to extrapolation, where we estimate values beyond the given data points. In this example, we will explore extrapolation, a method used to estimate values beyond the given data points. We are given 2 points, 1, 2, and 5, 7. Our objective is to calculate the value of y when x equals minus 2. Let's go step by step. Step 1. First, we extract the coordinates of the given points, x1 equals 1, y1 equals 2, x2 equals 5, and y2 equals 7. Step 2. We calculate the slope of the line passing through these points using the formula, m equals y2 minus y1 divided by x2 minus x1. Substituting the values, we get, m equals 7 minus 2 divided by 5 minus 1 is equal to 1.25. Step 3. Now, we write down the x value where we want to estimate y, which is x equals minus 2. Step 4. We apply the interpolation formula, y equals y1 plus m times x minus x1. Substituting the values, we get, y equals 2 plus 1.25 times, minus 2 minus 1, equals minus 1.75. So, when x equals minus 2, the extrapolated y value is minus 1.75. Since the x value we are estimating is outside the given range of x1 equals 1 to x2 equals 5, this is called extrapolation. Unlike interpolation, which estimates values within known data points, extrapolation extends the trend beyond the given data range. In the next section, we will give an practical example where linear interpolation is used to solve a mathematical problem. In embedded systems, trigonometric functions like sine and cosine pose certain challenges. First, they are computationally expensive, meaning they require significant processing power. Second, the necessary mathematical libraries might not be available on resource-constrained microcontrollers. A practical solution to this problem is to approximate trigonometric functions using interpolation. For example, let's say that we need to compute the sine function for angles between 0 and 90 degrees. Instead of performing direct trigonometric calculations, we can store a set of pre-calculated data points and use linear interpolation to estimate values in between. On the right, we have a table listing some sampled data points for sine of alpha, covering angles from 0 to 90 degrees. On the left, we see a graphical representation. The black curve represents the real sine function. The dotted line represents a linear approximation between the sample points. The orange dots mark the actual stored values. When an input angle falls between two stored points, we can use linear interpolation to estimate the sine value, achieving a relative error of less than 2%. This approach is widely used in embedded systems to reduce computational complexity while maintaining sufficient accuracy for most applications. By leveraging interpolation, we can implement trigonometric functions efficiently, even on hardware with limited resources. Thank you for watching our tutorial on linear interpolation and extrapolation. For any questions and feedback, use the comments section below. Don't forget to like, share and subscribe for more engineering content.